right, looks good. People are settling. There are not that many people outside. So we're continuing with the do-it-yourself style session. I'm very excited how that will work out for network monitoring. Let's welcome our speaker.
So I think this, mic is still working. Hello, everyone. I'm Joe Slowik. This was a really nice follow-up, or whoever did the scheduling did a good job in pairing this discussion with the previous discussion, because really we're talking about how to do things yourself to improve your security posture. Nothing I'm going to talk about today should hopefully be completely new, but perhaps in putting different open source technologies and other sorts of things that you can go out and grab repositories for right now, you can do a much better job in securing your organization and providing additional measures for detection. So who am I? I'm Joe Slowik. I'm a threat intelligence analyst and adversary hunter. In fact, that's my title right now. I don't know who made up that term at Dragos, but I do adversary hunting work for Dragos, finding the bad people and determining ways to stop them. But prior to that, I ran the incident response team at Los Alamos National Laboratory, so the U.S. Department of Energy. I was a naval officer prior to that for about 5 years, and then if you go way back, I was actually a philosophy major in school, and I dropped out of graduate school when I realized that getting a PhD in philosophy was a shortcut to a life of poverty and other sorts of things, especially in the United States. So enough about me, let's talk about where we're going to go. So we're going to talk about network and host visibility and trying to leverage network to improve what we can see from a host-based perspective. Sounds contradictory, but bear with me, it'll make sense, trust me. Trust me. Then in order to show you that this actually does work, we'll talk about some use cases tied specifically to the ICS realm. So I do ICS security research right now. As my full-time job, though these techniques are certainly applicable elsewhere, but they're especially useful in the control system environment for reasons I'll get into. And then we'll also talk about some limitations to this approach and other certain ways that you can work around them to make it more robust for your own uses. So how did this conversation start? Well, it started out with a tweet, as so many things seem to do these days. But anyway, regardless of what you think of Mr. Malware Jake, he had this poll up a while ago for like, which do you need more, network or host visibility? My answer is, well, why not both? Really in looking at the problem set for advanced threats is that you have artifacts that you're going to observe on both a network and a host level, and not having one means that the other is going to be disadvantaged to a certain extent. You're not going to get the complete picture. So if we need both of these, though, you don't often find them all the time, at least not to the extent that you want. So host-based monitoring is certainly vital, but in terms of rollout deployment, it's a lot less mature. Like we can talk about using the Beats modules, doing sysmon forwarding to Elastic, and all sorts of other open source solutions, or buying really pricey endpoint solutions like your Carbon Blacks or your Falcon Strike, whatever, I can't remember the name of it off the top of my head, but big commercial products that cost a lot of money. We know about these things, but they're still not out there, especially from a centralized logging standpoint like we'd want them to be. Network-based monitoring, however, is a lot more mature, and not only that, but the nature in which we deploy it, it's typically sitting on centralized appliances that we, IT, hopefully IT security, have a lot of control over. You control the network infrastructure, where the firewall is, and how those logs work. But unfortunately, that's likely to be a less complete picture of things because you're going to miss out on all those host artifacts that you really want to get your eyes on. So the best answer really is to use both of these complementary to one another in support of one another to get a complete picture. But unfortunately, you're not always going to be in that position. So visibility certainly depends upon what kind of environment that you're in. So if you're in a very well-funded, got a lot of smart people working for you that have lots of time on their hands to roll these sorts of things out, and you're in a standard Windows domain environment, you have all the security tools you could possibly want to play with and potentially the budget to make that happen. But if you're not in that sort of an environment, like say you're running an industrial control system network where you have a combination of Windows Server 2003, yes, this does happen, all the way up to maybe, if you're lucky, a couple of Win 7 devices that are out there, and then some other hodgepodge of systems. There's no Active Directory, your logging is poor. What do you do in a situation like that where your host visibility is nil, to say the least? Well, there's different challenges to this, but also the nature of the network provides some opportunities that give you options to approach the problem. So, host might be higher fidelity ground truth, difficult to push out and manage for reasons I talked about. Network, even when you're talking about an environment like, the dirty, hard to manage control system environment I just referenced, you still have switches and routers. You still have the capability of getting traffic off the wire or passively monitoring things. So what if we can use that to try and shed some light on the problem that we're trying to solve, to bridge the gap, so to speak, between the visibility that we have and the visibility that we want. So let's use network to try and capture as much of host as we can. So you can leverage network visibility to try and get a grasp of what might be going on further down the line at that host-based level. So files moving across the wire, or even commands via visible protocols, or sort of a hybrid between the two. You see a lot of advanced actors, we'll talk about one in a little bit, that love using things like scripting objects, shell scripts, etc., to automate their commands, and you can pull the content of those if you've got full capture on the resulting communication link. But even if clear text is unavailable, you still have options for tying together how different nodes are communicating to one another to tell a story based upon protocol and traffic type of what might be going on. So to try and put all these things together, what you want to do is leverage the attacker's dependencies for how they have to actually interact with your network in order to gain visibility and insight into what they are doing. So the data commands must come from somewhere. Exfiltrated data has to get out and go to somewhere. Identify what critical nodes have to be passed in order for these things to take place, and then identify and parse traffic at those strategic midpoints. So if we were to look at this in a diagram, so to speak, somewhere out there you have an adversary, whether it's some sort of external C2 or you have an internal compromised host. If you're talking about something where you have two separate networks, like a control system network and the IT or business network, the attacker has to control his or her, it's probably a he, unfortunately, implants from somewhere. So take advantage of the fact that they need to communicate from what they control to what they need to influence or where they need to gather things from. So that means they have to pass through one or probably more network choke points. So these could be inter or intra-network based, and it gives you options for monitoring and capturing. Once you identify what those choke points are and you can increase your visibility, again, these are presumably devices that we have far more control over than we do on every endpoint in our network, then you can monitor what goes from the adversary to their target or their victim. Victim seems like a shading thing as being completely innocent, but if you open a fish and enable macros, you're not as much of a victim, in my opinion. You're still a target, though. Anyway, so you see things like commands, second stage is being passed down, or in the reverse order, exfiltrated data if you're talking about an information theft case or whatever. So seeing the interplay between the two endpoints and monitoring things in the middle gives you at least the option to start determining what sort of things are being passed between points A and points B. So how do we do this then? Well, we already talked a little bit about Bro in the previous discussion. We're going to talk a little bit more about it today. So Bro is awesome. It's an open source network traffic analyzer. I grew up speaking Snort. I was in Snort shops my entire life up until I started work in the Department of Energy, which lo and behold, Bro was initially developed at Lawrence Berkeley National Laboratory, go DOE. And we started using it more robustly in that environment. I will confess, I am not a Bro expert. I am still learning how to use it after trying to shrug away my history of using Snort-based rule sets, but Bro gives you the capability of diving into traffic flows and content to the extent that Snort just doesn't allow. So it gives you much more flexibility in terms of what you can analyze with traffic and what sort of data you can suss out from when you have full traffic capture. More importantly is that there's a lot of flexibility and continued development that's all open source around Bro as a network monitoring solution. So you get tons of flexibility with almost zero developmental effort on your own end in order to deploy it and make it functional. And it was referenced earlier that Security Onion can be deployed, no problems whatsoever, as being a easy turnkey sort of solution to get up and running on this so long as you can point a traffic feed at it. But one of the most important things that Bro allows you to do, and that starts getting us into the mindset of capturing host-based artifacts from a network capture, is that you can do complete file carving out of Bro. What would normally be an arduous and, quite frankly, a pain in the ass sort of task if you just have a packet capture and then carve a file out of it, especially if you're not talking HTTP, but something like SMB or whatever. Bro understands the protocol. It can carve files out of that stream and just drop it into a directory for you to do something with. So the only limitation on this is that, as long as Bro has a processor for it, it can carve things out of it, so long as that traffic's not encrypted. We'll come back to that point in a little later, since it's a very non-trivial one. But a stupid simple example of file carving with Bro is this. Just carve everything that you see for every preprocessor that you have or every protocol you understand and drop it into the working directory. Now that could get a little noisy and a little overbearing fairly shortly, but this isn't hard in order to structure. If you want to get a little more complex, and this is in a little bit of an eye chart, the slides will be available later, you can certainly build things out so that you capture artifacts like hash values, add a timestamp, add the MIME type based upon the file, etc. It's really how much work are you willing to put in to get out data that you need. But the important thing is that, yeah, I mentioned that you can do things like just get a list of hashes. Just getting a list of hashes and checking against a known dirty list or doing a virus total check, yeah, that might be helpful to an extent, but it really is not going to get you where you need to be. Really what you want to do is pair that ability to carve data out of the traffic flow to some sort of analysis engine to start looking for things. So your options would be like you could sort of do a roll your own network inline sandbox. That's a little expensive and hard, but it's possible. A little more lightweight, though, is that you can start deploying things like detection scripts or Yara to start looking for items of interest that happen to be flowing within the traffic that you're monitoring. So, to overview the file carving scope, look for and pull anything that Bro has an analyzer for. So your common protocols, HTTP, FTP, SMB, etc. If Bro can see it, you can grab it. Now this is not trivial to say that, oh, Bro can do everything. In a customer environment, we just ran across the limitation that, oh, Bro doesn't have a TFTP parser. Now, some of you might be wondering, is like TFTP, who still uses that? Well, a lot of people, unfortunately, especially in a control system environment where you talk about doing things like updating the firmware image or the operating system on, say, a network appliance. So that's something we're working on right now, but at least you have the flexibility of writing an analyzer for the protocol of interest and then deploying it to get this functionality. So to look at this in a visual manner, so you capture some traffic, items get carved out of that traffic stream, some initial filter to whittle down what you are looking at to the items of key interest. So maybe I only want PE files, maybe I want PE files and document files, maybe I want to see PowerShell scripts if they're available, etc. But something to scope what you're grabbing so that you're not just getting every single HTTP object and every JPEG and GIF or GIF? Anyone? GIF? We can find it out later. Anyway, but something to limit the scope of what you're looking at so you don't drown yourself in data. But then once you've subsetted what you're analyzing, leverage tools in whatever engine you're using to analyze to identify malicious or suspicious activity. And this is where things get really interesting. So your detection possibilities are likely vast. What I'm going to focus on today mostly is Yara, but also talk about some detection scripts. So Yara is, you commonly looked at as malware detection. I'm going to try and move away from just looking at Yara as an antivirus replacement, but you can really extend it to just look for strings of interest or patterns of interest. You can even use it as a form of data loss prevention by looking at traffic leaving the network and, hey, does this happen to have a text header in it that says top secret // SCI code word, whatever goofiness or whatever. Like you might want to see that leaving. You might want to wonder why that's on a visible network in the first place. But anyway, those possibilities exist for doing that level of analysis. You can pair that then with some script, very simple scripting to unpack items or to do additional layers of analysis or to unpack something that is a packed executable to give you further visibility. So Yara is something that I use all the time. So I call myself a malware analyst in a lot of respects, not a reverse engineer, because I don't spend all day, every day, elbows deep in IDA Pro doing stuff, but I like to think that I can pull apart malware and identify things of interest. And Yara is really the best way, in my opinion, for codifying what knowledge I gain by ripping apart a piece of malware, suspected software, however you want to phrase it. Yara gives me a flexible and powerful means to look for items of interest and sort of set them down in a easily used format that can then go out and search for these things in the future. So as an example, like here, this is a couple of rules I wrote to catch NotPetya. So it includes both string and binary form pattern searching. So there was the embedded PSExec that was within NotPetya. Really easy to find that. Look for multiple MZ headers and then the accept EULA string within the binary itself, like that shouldn't be there regardless or whatever. Why do you have embedded PSExec in something? Probably want to look at that. But then there was also the shutdown scheduling routine that was coded into the file itself that changed a little bit. You can see a little wildcarding in that example, so that's an example of flexibility. But the function itself, outside of putting it into another compiler, and at the end of the day we're all sort of lazy, really stuck through all the iterations of this that I was able to spot. A little more complex example, so this is Olympic Destroyer. And this relates to the service stomping or the service rewrite that was the final step in causing systems to not be able to reboot because your services are now borked. You can go as complex as you want in here. This is actually a really tight signature, even though it looks like there's a lot of wildcarding going on. And I found a lot more samples than were published for this that were also Olympic Destroyer as a result. But you're looking at this and it's like, wait a minute, I thought you said you were going to talk about Yara not just as an alternative to AV, and that's really all that these are so far. But what about something really simple? What if I just want to look for all files that have a compiled time or a timestamp that is, let's see, I'm trying to remember what that breaks out to. I think that's like 1990 or 2000, a timestamp before the year 2000 or in the future. You should presumably never see this. Maybe in your environment you have some really old binaries lying around, but seeing something that has a timestamp of January 1st, 1970 or whatever, like, okay, that's a timestamp that's been wiped out, or it says it was compiled in 2038, probably want to analyze that. So this gives us an idea to look at something that's not known malicious, but gives us an option to start flagging things that are just really suspicious. So now let's put this all together. So host-based artifacts, like seeing executables fire and the details around that, it's really one of the main things that we like getting out of host-based logs and host-based forensics access. But we can get that by capturing them en route to targets via network-based monitoring. So capture the traffic, leverage something like Yara in order to identify items of interest within that traffic stream, and then begin your investigation from there. So let's put this in practice. Get sensors in place, like get some scripts put together, et cetera. What can we actually look for then? Well, the options are pretty various because it's really left up to how you want to put this together. So the answer is it depends. What does your environment require you to look for? What is it that you want to see? If you're talking about a fairly stock Windows environment and you're not worried about big bad nation state advanced persistent threat kicking down your door, you might not even need to go this complex, although you could use this as a very cheap alternative to some much more expensive commercial solutions. The example environment I'm going to talk about is industrial control systems. Why? Well, in addition, that's my job. It's also a really good environment for this sort of approach because antivirus coverage is kind of spotty, so you need to make up for the lack of traditional security coverage. Host coverage is incredibly rare to non-existent in these environments, but network capture is quite good. So we have a lot of the ingredients needed as well as the reasons to pursue this approach that would make it successful. So first, let's talk about crash override. So those who were in the discussions yesterday heard that mentioned in the attribution talk. Crash override was the malware framework responsible for the 2016 power outage in Ukraine. It was a purpose-built industrial control system attack framework with various payloads targeting different ICS functionalities. Well, that's actually misspeaking there. Different protocols for different types of ICS equipment, in this case targeting grid operations for the substation in question. Now the attack itself, was a multi-staged event. Lots of work went into this. This wasn't something like a Olympic Destroyer WannaCry, set this forth, let it do bad things and walk away. Instead, the adversary needed to get into the ICS network, establish some sort of foothold so that they could survey the network, enumerate systems and protocols, and then once they knew what they were dealing with and had the accesses required to deliver their impact, then deliver the attack. Everything prior to this takes time, effort, and dedication to make it work. This is not something that happens in 24 hours, but more likely over the scope of several months. Now, what we want to focus on in this approach is not necessarily blocking any one of these items, since that's sort of a host-based thing, but looking at each of these connection points between different stages of the attack as data moves from attacker-owned infrastructure to victim infrastructure or moving back and forth between the two. So how did crash override function within the network? Well, they moved around through what may be seen as quite basic methods, living off the land functionality like using netuse. So we saw a lot of, there were I don't know if this has been too much emphasized in public, but subsequent data that Dragos and myself have recovered on crash override indicates that the adversary compromised a handful of Windows Server 2003 devices they are out there, running Microsoft SQL Server and use the XP command shell from the database compromise to then get code execution on subsequent hosts. So you see lots of XP command shell, net use, pick a target, harvest credentials. There was a version of Mimikatz deployed for credential harvesting, and then go from there. There were also scripts that were used, and peeking beneath the hood a little bit, all it is an automation of a lot of these same commands. Net use for file movement, file execution, etc. So what's going on here? Lots of living off the land. I didn't have a really good example to show here, but also using PSExec for process execution, lots of scripting, etc. All of this is going to create a lot of noise in things like SMB. So we have a protocol trail, we know how the adversary is going to operate. We also have an idea for a more general sort of behavior that any adversary may use. Well, let's zero in on it and see what we can do with it. So our detection strategy is like, let's look for that file transfer activity as a means of gaining insight for what's moving through the network. So something that we would typically rely on a host-based log to find out, but in this methodology, we will try and capture that data through midpoint capture. We'll parse those files and look for malicious or suspicious content, and then take advantage of that adversary's requirement that they have to drill down through multiple layers of the network to get from adversary initial infrastructure through the victim IT network all the way into the ICS network where they want to deliver their malicious impact. So Bro, as it so happens, has a native SMB module that's out there that you can just enable to have good things happen. This has a few alterations in it. I had to snip some of this out, but this is something that you don't necessarily have to put in place yourself. You can modify it, certainly, depending on what you need to do with it. But right now, you can grab it out of either a GitHub repository or use the one that's in the default Bro config, and you're capturing traffic on SMB. All right, we're good. So next, let's look at the malware in question, or in this case, the software that is ICS-oriented that just so happens to do malicious things, because when you look at it, it doesn't really fit the mold of malware in the sense that AV would pick this off. So we've got the destructive module to impede restoration as well, plus some off-the-shelf items like PSExec, and they used a UPX-wrapped variant of Mimikatz. Nothing too fancy there. But I say not really malware because around the time that this first hit, and what is the date on this? So yeah, 12/19 when so someone, thankfully, for us researchers, uploaded this to VirusTotal the day it happened. Yay. But you can see that other than getting things like Wisdomize, which what does that tell anyone? It tells me nothing. Wisdomize is a junk signature and seeing a few other examples like that. But otherwise, your AV engines weren't really meaningfully picking this up at all. So AV is not helping you much here. Not surprising. It wasn't designed for these sorts of threats. And looking at the software in question, that was one of the ICS-specific effects modules. It's outside the scope of standard commercial antivirus. So there's not so much to look for there, but there's an awful lot of interest if you dig into the file that is of interest from a purely ICS perspective. And it's that contextuality that this flexible approach towards monitoring lets you embrace because you can design your own. So adding some custom or tailored to your environment detection at midpoint would identify the payload prepositioning before the attack is delivered. So from a very specific standpoint, and this is on the Dragos GitHub repository, was included in our report from, wow, time flies, July of 2017? But anyway, there are two different variants. So on the one hand, you have some byte pattern activity for the configuration reader that was built into the main crash override module that would read the config file that would tell the malware how to execute the specific ICS attack payload. Okay, that didn't change very much, and so that was a pretty good bytecode signature to use. But also, you know, there is just interesting language in these meant to both provide output to the user that their payload is working, and debug strings that can be tailored off of that are unique to the ICS environment. So seeing the IEC 104 protocol called out, master-slave relationships for communications, as well as referencing a log file, like, okay, those are also items. And by abstracting from that a bit, you can identify more general terms to start identifying in traffic, and we'll see some examples when we start getting into Trisis in a little bit in a few slides. But to close out crash override, we really want to build out environment-specific defense that's suitable to what visibility we have and suitable to what we're trying to defend. So implement these at those network choke points because we know that the adversary must navigate through these in order to reach their objective and detect suspicious items as they traverse those in advance of the attack. So you've gotten a breach, you haven't prevented a breach, but you may have prevented the lights from going out for a couple of hours, but I'm sure the people in Kiev in December didn't appreciate that very much at the time. So really it's knowing your environment and what's going on there and targeting those attacker dependencies to get a better visualization or a better understanding of what's going on in the network. So next, we'll move on to Trisis. This is a more recent event. Well, more recent in terms of discovery for most of us, happened in August of 2017, was the third ICS impacting malware, Stuxnet, Crash Override, and then Trisis. What's unique about Trisis, it was the first to target safety systems, which, to paraphrase Bird Person for the Rick and Morty fans out there, is very much a dick move. These are the sorts of things that you target if you want to hurt someone or destroy some equipment. Not cool. So just people shouldn't be playing around with these. The functionality of what was recovered, and this is something in talking with the folks at FireEye who have done the hands-on incident response as well as from the things that we were able to recover, is the malware that's available and all the components that have been recovered thus far are enough to set up basically a rootkit, an in-memory backdoor on the targeted safety system. And that could allow for lots of options, but we didn't see something like Crash Override where we had a automated framework for deploying some sort of destructive effect. So it's more getting up to the point where you could do such a thing, but not there quite yet. Now, the attack framework, you had to penetrate the ICS network, establish a fault. Wait a minute. That looks just like Crash Override, doesn't it? In fact, it is the same sort of attack pathway that you have to go from your initial, wherever your adversary is coming from, all the way down to that point in the network, fairly deep, where you can deliver your payload. What this means is that you get the same sort of dependencies of multiple choke points that the adversary must navigate, where you have the opportunity of setting up traffic capture and monitoring. So the same similar challenges apply for the adversary in establishing C2. They've got to make sure they dig into the network quite far and then maintain communications. And then once all of that happens, that ultimate payload isn't developed and deployed on the compromised host in the ICS network. No, it's migrated from that initial attacker infrastructure to the ICS network to the subsequent victim machine. Lots of places where you can pick this off as it moves its way down this path. So the malicious payload in question was downloaded. So if you talk to the ICS guys, like I would say uploaded, they say downloaded. It moved from the engineering workstation that was one hop away from the safety system, and it was facilitated by a compiled Python executable that knew what precise points in memory on the targeted safety controller, Schneider Triconex device, in order to upload its payload and insert the rootkit. So the uploads included the initial rootkit and then the subsequent backdoor module, et cetera, that were moved from the engineering workstation then onto the sys device. So we got an idea for how this attack works in theory. How do you defend against it, or how do you detect it? Well, the same sort of principles we've talked about ad nauseum already. Add detection at those choke points and look for items of interest that are traversing through them. So safety system controllers don't get updated hardly ever. It's something that's designed and deployed at the time that the plant is put into operation, and extensive testing is involved. You're not going to change the logic and the firmware on these things hardly ever, if at all. So when you see something that looks like a new firmware image or something that's migrating its way to the workstation responsible for interacting with it, that alone should be a signal that something might be up. And then adding further refinements to that data can identify that something truly is malicious or potentially malicious. So again, I'm not trying to make this into like, AV sucks, because a lot of people like doing that. AV is really good at what antivirus is designed to do. Antivirus was not designed to identify bespoke, narrowly tailored industrial control system targeting software. So in the case of Trisis, and got a couple of guys from Kaspersky jumped all over me on this one for implying that AV was not up to the task. It's like, I'm sorry, it just wasn't designed for this. It's not the right product. And Trisis was originally uploaded to VirusTotal way back when the attack took place in August. And nothing for detections for months. And up until the reports came out, there was nothing for detections outside of a few sporadic, crappy signatures like Wisdomize, et cetera. Again, antivirus isn't going to help you here because it's not trained or designed to detect these sorts of threats. So absent relying on solutions that are designed for your standard Windows desktop, what do you do? Well, just like with crash override, there are numerous aspects to this infection event that should stand out, that do stand out from an ICS-specific perspective. So there was a compiled Python executable used. You don't see Python in industrial control environments. Might sound amazing for all of us that live and die by Python these days, but it's just not a language that's represented, especially in a compiled form. Furthermore, the file headers and content for the malicious modules that get moved to the safety controller are very unique to that sort of software. There is some overlap if you start piecing them together with lots of other embedded devices like printer drivers, for example, but even still, you shouldn't see these sorts of things zipping around your industrial control network. So tailoring off of the file headers and some other patterns on those can at least trace potential firmware introduction into the environment. And if that doesn't relate to a known maintenance period or update period, you have a security incident to investigate. So on a general level, this is a pretty broad catch-all for just looking for compiled Python that happens to reference any sort of industrial control system technology. So all it's relying on is straight up strings, look for artifacts of the Py-to-Xe compiler, and does it reference any of these signals that I know would indicate that it's referencing some technology that I care about. So this is your general detection. Like, I should never see something like this, and if I do, that's a cause for investigation. So, here is your general detection methodology, but then you can dig a layer deeper, and these are specifically tailored to the malicious payloads that were used in the Trisis event. I've got a more general one of these that's out there as well, but it's the same sort of idea. But, looking for this specific file header within the bin file, file size less than 10 kilobytes, these are tiny files, and then let me see these sequences that correspond to the logic format of the Triconix controller. And from these, you could abstract then, so this was the, go figure I didn't label these. I want to say that this is imain.bin and this is inject.bin, but that could be reversed. Anyway, so that picks up the specific modules, but with some modifications, you can design this to look for any example of firmware and identifying when those get introduced to the network, which again should be a trigger to initiate an investigation. So what are our takeaways here? Well, first off, it's a safety system controller. You have zero host visibility on these devices, and you probably don't have much on the safety workstation that it connects to begin with. These are allegedly air-gapped systems, although, as we saw, the fact that this event even took place in the first place, that air gap is not as robust as you think it is. But nonetheless, you don't have much in the way of remote host monitoring or shipping logs off to a central stash or Splunk or something along those lines. But what you do have is you have multiple ingress and egress points to get to that target controller where you can see what is moving to and from it and to get an idea for what's happening there as a result of that visibility. So you can look for items that either never belong, like the compiled Python example, or only appear during known legitimate activity, such as the bin files that are used for the Triconix logic. Let's close, well, not close the talk, but close our examples, because I think, I'm doing okay on time, with a third example that's a little more general that might apply to some of your environments. So there's we define intrusion actor or intrusion activity by activity groups. It's a whole other conversation. You can pull me aside on that one later. One that we track is referred to as Dimaloy. You may have heard of some of this activity because it gets rolled into something that Symantec reported last year as Dragonfly 2.0. It's a group that was active in Turkey, Europe, and North America. So some superficial similarity to the legacy Dragonfly activity. Those are the guys who deployed Havocs and had a lot of success in penetrating industrial control system environments, but significant differences that we treat it like a separate group. Okay, full stop. That's academic wankery right there. Main thing is part of the ICS intrusion involved with the Dimaloy actor was the exfiltration of HMI screenshots. Screenshot exfiltration, why is that interesting? Well, you don't see too many JPEGs or PNGs coming out of your industrial network. Well, not only that, but screenshots, if you think about it a little bit, are typically identified by a couple of interesting metadata points. So Dimaloy itself, their modus operandi, their method of operating, initial access via phishing and website compromise. They deployed a lot of malware, mostly a lot of off-the-shelf sort of stuff that could be confused, a lot of other criminal activity, et cetera. Nothing really interesting there. And then at the final information collection stage, they deployed a credential grabber that included the Mimikat source code and did a few other goofy things in order to harvest credentials, a document vacuum cleaner, I guess, because it just would look for any sort of spreadsheet or whatever, zip it up and send it off. But then there was also the exfiltration of screenshots. So you might think like, well, what importance is a screenshot other than saying like, haha, screenshot of your box, I compromised your system. Well, if you think about it, a human-machine interface device in an industrial control system network is going to give you an overview of the plant process, the plant environment. As a initial intelligence collection point, it's actually quite valuable, and it can identify subsequent network nodes that you either need to compromise in order to achieve a goal, or if you're just simply committing industrial espionage, can give you an awful lot of information for how that process is designed. So it's actually a very valuable piece of data for these guys to have grabbed. Now, screenshot activity within the ICS network is a good alerting point. How do you actually alert on it, though? Well, you don't have host logs, and even saying that, I don't know how you really pick that out in host logs too well anyway. But something that doesn't get picked up by a security solution either. Like, I don't know of a carbon black rule or of a pick an EDR product or whatever that's like, oh my goodness, we got a screenshot. Like, I've never seen that before. If I'm wrong, correct me afterwards or whatever, and I'll certainly adjust this. But it's typically not activity that we associate with maliciousness, but it's a good indicator that someone is in the process of doing something you would otherwise they not do. So what we can do, though, in order to identify this is deploy Bro to look for files that match a screenshot profile, leaving the network in question. So how do we identify what a screenshot is? We'll look for image files that match known desktop resolutions. Because unless you have someone who's opening up Paint and resizing things on the fly, chances are you're only going to see things in about 5 or 6-ish different combinations of resolutions, especially when you're talking about a very narrow set of devices such as human-machine interface devices in an ICS network. So this is kind of a stupid, simple alert that you can design. So identify that there's an image file on the wire, capture the file via Bro, and then do a simple EXIF grab in order to see, does this image file match a screenshot resolution? So there's not a whole lot of complexity here, but at the same time, if you ever see this in the environment that this rule is tailored for, something not cool is going on. Either you have an engineer who's trying to make a PowerPoint for their next presentation at a conference in Las Vegas or something, or someone's trying to steal data from your network. So we could apply Yara to EXIF results or to other ways of grabbing file metadata, pattern off those common screen resolutions, and use it as a useful data point. Now, I've thought about this from an IT perspective, and it certainly seems like there might be some legs to it, but I would like to add in additional sort of logic gates to make this into an effective or useful rule there. But again, tailored to the environment that this is being deployed in, it's very useful. So we've gotten some examples. We've talked about like, whoa, use Yara and Bro, the world will be a better place and you'll see all the things. Well, ultimately, this approach really is just an approximation. So for those who have read The Republic, as Plato said, at the end of the day, we're only kind of glimpsing shadows on the wall of the cave. This isn't a replacement for host visibility. It's really just trying to make the best of what we have. So if you have an environment or you have the flexibility to do more from your network side, these are options to try and reduce that invisibility or increase your visibility and respond and gain awareness of what's happening in your network. Now, there's some key weaknesses involved in this, though. I already mentioned encryption. We're going to talk about compound file types. That's actually not as big of a deal, but it's something that needs to be considered. And then some engineering perspectives leading up to, what does this really give you in the end? So first off, what's the simple, stupid way to defeat this? Well, encrypt all your traffic. At that point, I'm blind. So what's more important is a lot of adversaries are moving to encrypted communications channels. Gone are the days of the custom XOR routine or some other crazy encoding schema that's designed from scratch, and I'll just get a let's encrypt cert and encrypt all my traffic and, you're done, basically, dead in the water from a network traffic analysis perspective. It's not as applicable in some environments, though. So one thing that's nice if you're looking at this from an intra-network perspective, like in the industrial control system environment, encryption, for better or worse, is incredibly rare. It doesn't happen that often. You might see HTTPS for grabbing things like software updates, which you have direct internet connectivity then, which is not a good thing either. But a lot of the protocols of interest for that moving around the network aren't encrypted. So it might work very well there, but you're probably going to be dead in the water for your traditional Windows domain environment. But there are workarounds. So one thing that I like to look at is, again, going towards, can I get a glimpse of the information to figure out something worth alerting or acting on? Bro allows you the option of capturing certificates associated with encrypted traffic. Well, why might you want to do that? Well, you could identify new or unknown certificates as one option. You're probably not going to enjoy that a lot, especially if you're doing this for environments that do a lot of web browsing. But what you can do is look for certificates associated with things that are suspicious inherently. So, I have Let's Encrypt certificates. That's something, it's not an evil service in and of itself, just like Tor isn't evil, but it's certainly leveraged by a lot of people as a cheap and easy way of getting the job done, and maybe you shouldn't see any Let's Encrypt certificates for egress traffic from your network. You could also look for things that are self-signed or even known malicious items. So in a past life, I did a lot of work on the APT28 group, Fancy Bear, however you want to call them, and they had a dead giveaway pattern for how they created their SSL certs. It was London, UK, I can look it up again or whatever, but they had the cert metadata pattern was the same for all of their C2 nodes. So identify anything that matches that, and like I have a suspicious certificate associated with SSL traffic that I know is associated to a known bad actor. Okay, you've cleared up the image a little bit by having that metadata look. Now you have something to investigate, whereas before it's like, oh, it's encrypted, I can't do anything with it. Another thing you can do Ssl Intercept. This is a touchy subject. So it's justifiable, in my opinion, given the shifting landscape. Your users are going to hate you. Your lawyers are probably going to hate you too if you try and pitch this. But it's something that needs to be at least discussed from a gain-loss perspective. Like, yeah, we can do this, but then you got to worry about your security team stealing people's banking data and privacy and all these other things. But if we don't do it, it means that all of these bad actors, from APT to ransomware, script kiddies or whatever, can do whatever they want on the wire and we can't see it. It's something to discuss, but for many reasons, it's not going to be practical for most people. Another thing you can do is identify host workarounds if possible. So certainly you can identify host workarounds from the standpoint of host-based logging. That kind of shifts the conversation back to where we started, though, and defeats the purpose of my talk. So we're not going to talk about that. Instead, what we will talk about is something interesting that I just learned about a couple of months ago. So something called the JA3 project, which is designed for host and application fingerprinting. This was something put together by John Althaus at Salesforce. It was presented at the Art into Science conference a couple of months ago. And it allows for the identification of hosts and applications based upon the certificate metadata in the traffic stream. So it's a way of fingerprinting what the application is that happens to be talking back. So maybe it's not the browser, maybe it's someone's deployed, remote access tool, remote access Trojan, or something else. This can allow you to get a viewpoint of what sort of encrypted endpoints are in your environment and look for ones that are anomalous or new. So again, this is relying on network traffic capture, but it gives you at least some insight into what might be going on within the host environment. So I strongly encourage everyone to take a look at that. It's a really cool project. I need to start playing around with it more myself. So we talked about encryption. That's a hard one, but there's options. Compound file types. So the approach that I talked about right now works really well for PE format, your legacy Office documents, things of that nature. Doesn't work so well with compound file types like archives, the XML format document types like docx, XLSX, etc. So what do you do about those? Well, it's simple. Put a script in there and unpack the things. So first, identify the file on the wire. Carve it from saved traffic, okay. Do a MIME type identification to shunt it off to the right processing script. So, identify script by mile type, extract, expand to a temp location, and then profit. So whether that's unpack UPX, unzip a zip file, or unpackage a docx file, lots of options for this. You just need to be aware that they're out there and put something in place to handle it. So here's a really simple example. I did not modify this from when I put it together in my previous job, and I whipped this together in 20 minutes or so. So it is ugly, but it works. Just identify all docx types within a directory, pass it a YARA rule, unpack them, scan every individual unpacked item, plus it does a grep for IP addresses, because this is when I was looking at the fishery, not exploit, but whatever, the fishery kit for injecting things into document files, and let me know if there's anything there, and clear it up at the end if you see nothing. So this is 15, 20 minutes worth of bash that solved that problem right there for trying to identify malicious macros in Office files or the fishery kit embedded within Office documents. No big deal there, you just need to be aware of it and implement it. And make sure that you're deleting things after you're done too, because you can, if you're doing this for email for like a 25,000 person network and everyone likes attachments, this will take up a lot of space fairly quickly. So yeah, doable, requires effort. Key is just finding a sustainable workflow. Won't overtax storage, won't overtax processing, and know what sort of requirements that you have in question at the get-go so that you are applying this in a sane fashion. The next items are more sensor-based or architecturally based. So this approach works really well when you have sensors in line to capture traffic. Network edge is typically covered fairly well. That gets you C2, downloads, uploads, etc. Internal traffic, less so. And we've talked about some examples where it'd be really useful to sort of see that SMB traffic moving back and forth as a way of carving files as they're moved through, like, C dollar share, etc. So what do we need to do there? Well, try to create more choke points in the network so that you're enabling more of this monitoring. That's why the ICS network was a nice place to start for this idea, because you have a lot of natural choke points, or you should. You didn't in crash overrides case, as far as I can tell, thanks to those SQL servers, or MS SQL servers. But typically you have, just by virtue of functionality, the network is carved up into different enclaves, and you have different network appliances that are physically segmenting those. So lots of different points where you can capture traffic. In your Windows domain, you might not. You might have a very flat network. We all know that flat networks are bad. We also all know that flat networks are more common than we'd like to admit. So you could either fix sensor coverage issues in order to try and put more things in line to detect these sorts of things, or you could look at deploying VLANs as a virtual option in order to make this work. Ultimately, this is sort of an architectural item, so it's hard to implement. It's kind of a pain in the ass, but it's something that at least needs to be discussed in order to make such an approach worthwhile. But if you do this, not only is something like what I've discussed today applicable, but you get better visibility into things like lateral movement and other items once the crunchy outer shell of the network has been pierced and you're into the gooey, chocolatey center. The last thing is, and I've gotten this sort of feedback before, is like, oh, this is all well and good, but this is reactive only. You haven't stopped anything here. You're just detecting that bad things have happened. The damage is already done or in the progress of being executed. Yeah, that's true. But you know what? You might be reacting, but I will tell you this, if you're doing this sort of approach, you're detecting things a little earlier than you did before. That might not seem like much, but I bet you for the guys who were working at the distribution station in Ukraine back in 2016, they would have loved to have seen this a couple of weeks before the lights went out and prevented that from happening or start responding then. Even more so for the Triconics event, where you had something that could presumably have led to loss of life or loss of equipment. So the goal here isn't to stop, because at the end of the day, we can't stop all these attacks. The goal is just to get faster. Picking off in network traffic means that we can hopefully identify badness before it spreads into poor coverage areas or poor recovery areas where we're really screwed when bad things do happen. So lastly, before we get into some concluding thoughts, you talked a lot about industrial control systems. I don't work in industrial control systems. How is this helpful for me? Well, I'm talking about ICS because that's what I do. So, we got that all right over. But a lot of these approaches can apply to your own networks, whether you have sensitive enclaves, such as, here are the keys to the kingdom, the holy grail, so to speak, containing all of the customer credit card numbers or critical institutional intellectual property, et cetera. It's like you can put a network choke point leading up to those, scan for traffic there, and apply a methodology such as this to gain an additional layer of defense as a result. So this idea might not be applicable completely to your environment, but aspects of it can be, especially when you start talking about critical network areas that you want to make sure are especially protected. So to close, let's not let the perfect be the enemy of the good, to paraphrase Voltaire. So imperfect situations require solutions of some sort, but we can never expect that the problem is going to completely be erased. Instead of crying that this is an insolvable problem or something that can never be completely addressed, let's instead look at what we've got to hand right now and see how we can make the situation better. In this case, identifying malicious activity, earlier in the attack chain so that we can decrease our time to response and improve our ability to remediate incidents as they're developing, as opposed to reacting after the malicious impact has been, actualized and we're, putting out fires at that point. So ultimately, what this approach really is based off of is, one thing that I like to close with is that there's this common misconception that, oh, the attacker only has to get things right once, the defender has to get things right every time. That is bullshit, excuse my language. Instead, the complete opposite holds true, because the adversary has to get it right every step of the way, and we, as defenders, since we're in the defensive track here, really only need to catch them once. The adversary needs to get into the network. He needs to establish persistence, has to survey and identify the network objective, deliver some sort of effect, and then complete it. That's a lot of things to get right and a lot of different places that we, as network defenders, can stop them or at the very least detect them. By applying approaches like this that look for those areas of visibility where we have better control, we can work on this model and disadvantage the adversary. So that's all I've got. I think I've got lots of time for questions unless my watch has stopped.
Thank you.